Okay. So welcome everyone to this session on strongly correlated systems and dynamics of quantum systems, theoretical aspects. So I guess more people would just trickle in, and also both in person and online. So we will start the first session now. There are two sessions with a lineup of very interesting talks. So the first talk is by Sthitadhi from ICTS, and he would be talking about measurement-induced entanglement transitions in certain tensor networks. So Sthitadhi, I'll give you a warning at 10 minutes.
Sure. Yeah. Okay. So yeah, thanks Shobhro for the introduction and also for putting together this meeting at such a short notice. So I'll say a few things about measurement-induced entanglement transitions in certain tensor networks, and this is based on a work that we did last year, published here with Adam Nahum, who was a colleague of mine at Oxford, has moved to ENS Paris now, Brian Skinner from Ohio State, and Jonathan Ruman from Bar Ilan. So before I actually get into the details of this work, just to sort of put things in the context, why are we interested in dynamics of quantum systems? Because, in some sense, in some loose sense, I can take the liberty of saying that quantum mechanics is operationally a theory of unitary dynamics and non-unitary measurements. And then once you take this view, then it becomes almost a natural question to ask that in time, how do quantum correlations or quantum information propagates in a quantum system? And it's not just or by now, it's not just some theoretical abstract that we're talking about, because most of these upcoming intermediate scale quantum devices like Google's Sycamore processor essentially do this, that in real time, they want to manipulate quantum states and so store and retrieve information from them. So that's why quantum dynamics. And then you can ask that why worry about quantum entanglement? Because in a way, it's some sort of an unbiased notion of non-local correlations throughout the system. That's sort of a cartoon view of what quantum entanglement is. And it's also of some practical value because you can actually use it to distinguish phases of matter. More importantly, you can ask things about how is the information shared, how is quantum information shared between different parts of the system, how robustly it is encoded, how prone it is to sort of errors and local perturbations, and so on. So with this sort of motivation in mind, I'll talk about the dynamics of entanglement in a quantum system which has both unitary dynamics and projective measurements. Okay, so to set the stage, the way many of us have come to think about quantum dynamics in the last sort of few years is via this notion of unitary circuits. So it's slightly detached, but not completely, from the usual notion of Hamiltonian dynamics that we are used to thinking about in quantum mechanics. But all we are saying is that we don't really care about a Hamiltonian which is governing the dynamics. We just want some set of unitary gates which are local in real space, which sort of give me the dynamics. And we sort of know that if the dynamics is generic enough, then if I start with a product state, then at some late times, if I bipartition my system into two parts, A and B, then there's a volume law entanglement between the two parts of the system, and that grows linearly. So this is for unitary dynamics, and this has been well studied, well established by now. And then the question is that once I have measurements, projective measurements puncturing this quantum circuit, then what actually happens? What happens to the rate of entanglement growth in such a setting? And this is sort of the question that I'll be sort of partially answering in this talk. So what actually is known via numerical experiments and heuristic arguments, quite compelling, is that there is a phase transition as a function of the measurement rate. So basically, if I am below this critical measurement rate, then at some late time, the two parts of the system again show volume law entanglement. Whereas if I'm at a measurement rate which is larger than the critical measurement rate, I actually end up with an area law type state. Of course, the state is dynamically evolving, but on an average, it remains, the entanglement between two parts of the system remains an area law. And you can sort of convince yourself that if the measurement rate is very high, then at any time slice that you look at, any qubit would have been acted upon by only sort of a few unitaries, which means that it will be entangled only within suborder 1 qubits around itself. So that basically is the idea, and there have been many, many papers in the last 3 or 4 years on this. I'm not even trying to list all of them here. So the question is about, can we actually find some exactly solvable model for this particular phase transition? And our intuition was that, well, coming from sort of basic statistical mechanics, that if we get rid of spatial structure in the system, we might actually be able to say something analytically and exactly. So that's why we went to this model, which we call an all-to-all connected tensor network. So the idea is that at any time t, basically any two qubits can sort of interact via a random unitary gate, which we take to be Haar random gates. And that happens with a rate of 1 minus r. And then with a rate which is given by a proportional to r, we actually put measurements, which are denoted by this broken world lines of the spins. So you can have two types of measurements. This detail is not really important, but you can do two things. One is you can project the spin up or down on the bond rule probability. This gives you some non-trivial correlated dynamics. Or you can say, as a sort of theorist abstraction, that and I'm only going to do first measurements, which is basically no matter what, I'm going to project the spin only up. This is basically experimentally equivalent to doing post-selection, but not really very feasible. Okay, so this is the model I'll be working with. And as soon as I go to this model, you realize that there is one sort of complication. Because this is an all-to-all connected model, I have lost all notion of spatial locality, and hence area and volume laws have no real meaning. So we need some sort of a new diagnostic for the phase transition if the phase transition is present. And that diagnostic happens to be the operator entanglement entropy of the non-unitary operator, which governs the time evolution. So the way you get this operator entanglement entropy is basically you do a singular value decomposition of this operator, you get the singular values, and then you compute the Renyi entropy in the standard way. Now let me sort of give you the result in two trivial limits and show that why this is a good diagnostic. So suppose I have no measurements, then of course V is unitary. So all the singular values are basically 1 modulo some normalization, and you get an operator entanglement entropy, which is maximal and extensive. Whereas if I actually consider a circuit which only has measurements, then basically there's only one singular value, which is 1, and rest of them are all 0. And in that case, I actually get a 0 operator entanglement entropy. So this sort of is a hand-wavy argument for showing or saying that why this is a good order parameter for the phase transition. Okay, so now the simplification that the all-to-all connected network tensor network offers is, to a very, very good approximation, you can actually visualize this network as a tree. So the way you do that is you consider each tensor network or each tensor as a node of a graph, and these world lines as links on the graph. So here, of course, I have slightly cheated and I have drawn it in a way so that it looks exactly like a tree. But what you can convince yourself is that the loops which make it not a tree are of size order log n. And that sort of tells you that locally you can definitely think of the circuit as a tree. Now, I talked about this measurement rate R. So a usual variable to work would be this probability P, which is the probability that a site is measured before any unitary acts on it. And what that essentially translates to on the tree is the probability that a given branch is killed after a particular node. So now, once we have this, we can first ask the question that is there a classical phase transition in this model which will act as a bound for the quantum phase transition? So the reason we are asking this is because you can sort of say that one measure of entanglement in your system is if I want to sort of separate the late time from the early time of the circuit, how many of these links I need to cut, and what is the minimum cost I can pay for it. So of course, when you have measurements, you want your cut to go through as many of these measured sites as possible, but nevertheless, you'll have to pay some finite cost. But if the rate of measurement is high enough, then you might be able to find a path or find a cut for which you actually pay no cost. And that essentially is a percolation transition, which is governed by the geometry of the circuit. And that is a classical phase transition. Because here, obviously, the circuit has been split into two parts classically. So of course, no quantum information can flow. So classical percolation on trees are well studied. You can actually compute the critical point, and you can also compute the critical scaling by analytically mapping it to sort of layered random graphs and so on. And just to make sure that these analytic results hold, we actually did a numerical simulation of the percolation transition on the full model, not on a tree. And everything seems to work very well. So we have partially gotten the phase diagram, which is there is a classical phase transition at this R, which is 0.8, and there's a power law scaling. But the question now is that can I have a quantum phase transition which is distinct from the classical phase transition, such that I have a classically connected but quantum disentangled tree. And to do this, we actually have to then study the entanglement properties of this stochastic or random tree tensor network. So the way we do this is we have this tree tensor network, and we want to quantify what is the quantum information flowing between the base and the apex of the tree. So I can, of course, write it, and I can think of this as some big tensor network, as some big operator, and do a singular value decomposition. Now, obviously, since there is only one leg sticking out of at the top, I have just two singular values. So this is sort of a pictorial representation of the singular value decomposition. And once I have that, I can basically say that I have a smaller singular value, I have a larger singular value, and I can compute the Renyi entropy between the apex and the base in this way. And for notational simplicity, we'll only work with the minimum singular value. For a tree with k generations, I'm going to call it zk, because once I have lambda min, I know what lambda max is. Okay, so now the added advantage of working with the tree is you can do things recursively because there are no loops. So if I have a tree with k generations, I can take a random unitary with some probability. I can put a measurement here, and I can stick these trees that you gave me to the bottom of the unitary, and I can get a tree with k plus 1 generations. So what that immediately means is that I can write down the z, which was the minimum singular value for a tree with k plus 1 generations, as a recursion relation, which is of course nonlinear, as a recursion relation which takes in input the zk's of the three trees. So that happens with a probability of 1 minus p, and it's 0 with probability p, which is when you measure the state. 2 minutes? Okay, fine. So what you can also do is near the phase transition, this is going to be very small. So you can linearize this, and these coefficients depend on the details of the random matrix that you put in. So just to give a pictorial view of what happens, so if I actually solve the linear recursion relation, and I look at the probability distribution of log zk, then in the disentangled phase, it quickly runs away to minus infinity, which means that zk goes to 0. In the linear or in the entangled phase, it sort of runs away to positive infinity. But you can say that, well, zk should be normalized, it should be less than 1, so why is it running off? And that's because I solved the linear recursion relation. As soon as I put in the nonlinearity, it sort of acts as a wall against which the distribution gets squeezed up. So that clearly shows that where you have the velocity of this traveling wave to be 0, that's where your phase transition is. So you can analytically do it. You can actually map it to a version of the Fisher-KPP equation that also appears in the studies of directed polymers in random media. Derrida and Schmoen had done a fantastic work on this in 1988. You can do all of this analytically, and you get a critical point, which is exactly this. And notice that this is very close to 0.8, which was the classical transition, but it's different. More importantly, you can study the nonlinear recursion relation and the nonlinear traveling wave equation, and you get an essential singularity like this, which is completely distinct from the power law scaling that you got for the classical transition. And sort of we did some numerics to verify this, all of this works. And that sort of finishes the phase diagram that you do have a quantum phase transition for the model with hard random gates, which is separate from the classical phase transition. You do have this phase where the tree is classically connected but quantum disentangled, and basically the phase transition is driven or governed by an essential singularity. It's completely distinct from the classical power law scaling that you get. So this is the phase diagram. Of course, you can play around a bit with the gates and to move this transition here and there. But it seems that this scaling stays the same. And we also did some numerics on the full circuit, not on the tree, quantum numerics, but on very small sizes to sort of, which were consistent with these results. I'm not showing that in the interest of time. And that sort of is, this phase diagram is my summary, and this is the reference. So yeah, thanks for your attention.
Thank you, Sthitadhi. Questions? Let me start with one. If I look at the dynamics of local operators, is there a sort of quantitative change or crossover from this intermediate regime and on the right-hand side of the classical transition?
In this model, no. But there are now models where this is implemented along with charge conservation. And there you seem to have another transition here in this phase, which is called the charge sharpening transition. So there what happens is basically when you have enough scrambling, you cannot define the charge, or you don't get a very well defined charge for the system locally, of course. But somewhere here, preceding the quantum phase transition into the disentangled phase, you can actually get a well-defined, or basically the states are almost eigenstates of the local density operator. So this is called a charge sharpening transition, but this is sort of very new. In this model, no, because in this model, everything is so heavily scrambled that all the local information is sort of washed out. But if you put a bit more ingredients, you can actually get this.
But even between this R quantum and R classical, and the right of R classical, there is no distinction in terms of any local operators.
So not really, because the thing is that, even if you are here and if you measure it at a particular time, what happens is that there has enough number of unitaries acted before it, even though it might lie above the minimal cut, that you don't get. You get basically something which is like an infinite temperature result.
I see.
So you can't. So, but with conservation laws, it seems you can, and that's something that's actually very new.
I see.
I also don't know the details of the results very well, but I see it exists.
Okay. More questions?
So here, basically, this entanglement just goes to 0, or there's some other sub, like it scales with n, right, in the entangled phase.
Yes.
And then it has some sub-linear scaling with n here.
Yes. So it's actually an area law here.
But how do you define the area? Because you have all-to-all connection.
Oh no. Okay. So that's why this is not a bipartition of the system in space. This is a think of it as a bipartition in time. So one way of thinking about it is that you have n qubits here, and then you have the whatever v that I wrote, and then you have the output set. Right? But now you can say that you are going to twist this, and this whole thing is your v, and you have, right, and then you have sort of bipartitioned the system like this. So it's an area law in this sense, and a volume law in this sense. So which is why here you see I have S by n, that actually is finite, but S by n there is 0. So the volume is still sort of as in the number of qubits is still well defined. So think of it as a bipartition in this sense. So, or think of the V as a state in a doubled Hilbert space, and then you are looking for the entire.
But if you, let's say, choose some sites, right, like
in this case you cannot. But actually, in this, if you do the same thing in a sort of 1+1D circuit like this, you actually get an area law with the standard bipartition.
No, but you can still choose some number of sites, right? So there is no locality, but you can still say that this is a fraction. Like let's say there is a fraction of sites that you choose.
Yes, but then it could then you won't see anything, right? Because it will talk to
everything. So it should always be just proportional.
Exactly. So in that sense, it will not work. But if you do it, which is why we had to do this operator entanglement thing.
Okay.
So in this picture, can one understand it in terms of the string tension?
Yeah. This is actually the entanglement membrane tension of this. So whether you draw it like this or whether you draw it like this is really the same thing. Yeah.
Okay. I think we are running short of time, so let's thanks to you once more.